going to take a look at some applications of exponential growth. The first thing I want to do is define the exponential growth function. Earlier in this class, we had taken a look at how to find half-life and doubling time using the rule of 70. And we used that rule of 70, that doubling time, that half-life, to approximate how much we would have given a certain number of time. What we want to do with this formula is we want to be exact. This formula will give us the exact amount of growth or decay based on a rate, a time, and initial amount provided. So our formula, Q equals Q naught, and that's how that's read, Q subscript of 0 is Q naught. Q equals Q naught times 1 plus the rate to the t power. Q is the final amount, Q naught is the initial amount, R is the rate, and T is the time. So Q just standing for the quantity, the final amount, quantity, final quantity, Q naught, initial quantity. What we want to be really careful of here is that the rate, if the rate's positive, we're just going to use a positive here. But if that rate's negative, we've got to remember to make this number negative, which in turn ends up turning into subtraction, 1 minus whatever that rate is. So that's something we're going to have to be aware of. Let's take a look at an example. Worldwide oil production has increased at a rate of about 7% per year from 1950 through 1972. If the production level was 520 million tons in 1950, how much oil was produced in 1972? So let's start by defining all the variables. I should note I didn't write it out, but we have a percentage here, and remember that percentages always indicate the exponential growth. We've talked about that in the past, so I didn't state that anywhere, but anytime we see percents, we know that's exponential growth. So we know we're using this formula. Let's start by defining all of our variables. The first number I see is 7%. That is a percent, so that must be the rate. Remember, we are going to want to use the decimal form of those rates. We always have to change those percentages to decimals to use when we have an R formula. This is very similar to what we did with the compound interest. Next, we want to figure out the time. Well, we have 2 years, 1950 and 1972. So to calculate the time, we're going to have to do a little subtraction here. 1972 minus 1950, that will give us 22 years. So our time is 22. And the last number we're given, because we want to know how much oil was produced in 1972, that's why we use that, not because it is strictly between 1950 and 1972, but we want to know from 1950 to 1972. Last thing we want to do is define the initial amount. The production level was 520 million tons in 1950, so I'm going to use a Q naught, or an initial quantity, of 520. Now you might say, well, shouldn't you use millions? But I keep in the back of my mind that this is millions of tons, and so what that means, once I get my final answer, my answer is just going to be in millions. So I'm just going to use a 520, keeping in mind we'll get a million tons at the end. So let's set up our formula. Q equals, Q naught is 520 times 1 plus, it is increasing because the rate was going up. We're going to have the 7%, so 0.07. The time was 22. And now I'm just going to type all of this straight into my calculator. And so when I type all of this in, I get 2,303.81, and our units would be millions or million tons. Million tons or million tons. So we can state, type it down here, the oil produced in 1972 was 2,303, or if we round, 2,304 million tons, which is equivalent to 2.3 billion tons, quite a bit of oil. Let's take a look at this next example. Current yearly U.S. inflation rate is 4%. If a gallon of milk currently costs $3, how much will it cost in 5 years' time? I do the same thing if I define all of the variables. So the first number I see is at 4%. So I'm going to have to write that as 0.04. I want to know in 5 years' time, so my time is going to be 5 years. And then the initial amount is $3. So that's going to be my Q naught. So we'll have Q is equal to 3 times 1. It is increasing, so plus 0.04 to the power of 5. And we'll type all of this into the calculator. We get 3.65 when we round it to the nearest cent, and that would be dollars. So we can state in 5 years' time, a gallon of milk will cost $3.65. That one was relatively straightforward, same formula, just plug everything in. Let's take a look at another example. A farmer sees a beetle infestation on her crops. Over 5 days, she measures the beetles to be increasing at a rate of 3% per day. She counts 50,000 beetles today. How many beetles were present 5 days ago? Let's define all of our variables. I see that 3% is jumping out at the rate. My time, we want to know 5 days ago. 5 days have passed. And we've been defining the Q naught. The problem is that 50,000 is what she counted today. We want to know 5 days ago. That's in the past. This is actually what we're looking for. We're looking for that starting number. We have the Q this time. The final amount is 50,000. So we're going to have to work backwards. Remember our formula, Q equals Q naught, 1 plus the rate to the T power. I'm going to plug the 50,000 in for the final Q. We're solving for the Q naught. And so we need to get that Q naught by itself. Let me create a little space here. To do that, we would need to find this green parenthesis here and then divide that entire expression over. Now if you want to do this in 2 different steps, you can. So if we take 1.83 to the 5th power, we'd get 1.159274074. It keeps going, it doesn't end. So we'd either want to write that entire thing down, or we want to use the answer feature of the calculator, so second answer, however your calculator works, that second button, second negative, however it works, to use that feature. Or what we can do, I can solve it in its current form. So I'm going to divide both sides by this 1.83. 1 plus 0.83 is just 1.83 to the 5th power. And I can type that into the calculator just as it is there. So 50,000 divided by 1.03 to the power of 5. And when we do that, we get an answer of 43,130.44. I'm going to round that to the nearest beetle. So 43,130 beetles. These numbers should make sense. They should, the order has to be correct. And so what we know is the beetle population is growing. It's getting larger and larger. So the fact that we started with 50,000 today and we're looking back in time, that number should be less. 43,000 is in fact less. So that does seem like a perfectly acceptable answer. The number of beetles 5 days ago was 43,130 beetles. And there's our answer. Let's take a look at one last example. Carbon-14 decays at a rate of 0.0122% per year. If you find an old relic that has 40% of its initial carbon, how old is that relic? So let's start defining things. We have a rate of now it is a 0.0122%, which means the rate is 0.000122. Because remember, we have to take that decimal place and we have to move it 2 to the left. It means it's a very, very small number. Carbon decays very, very slowly. That's why it's very accurate in carbon dating. We find an old relic that has 40% of its initial carbon. Wait a minute, we see another percentage pop up. Why isn't that the rate? This is not saying it's increasing or decreasing by that amount. It's saying that's how much we have present now. That's how much we have left. That is giving us our Q. Our Q is 40% of the initial. We want to know how old the relic is. So it's actually the time that we're looking for here. But there does seem to be a missing piece. Remember our formula, Q equals Q naught, 1 plus the rate to the T power. it seems like I'm not given a Q naught, a starting point. Notice that this was kind of awkward. We weren't given a number here. We're given that the Q is 40% of the initial. So we're dealing with a percentage of how much we started with. Well, we can always think about the starting amount as 100%. We start with the whole thing. We start with the whole initial value. So what I'm going to do here, I'm going to plug 40% in for the Q, 100% in for the Q naught. You can use either the percentage or decimal, it doesn't matter here. I'm going to use the decimal form just to be consistent. So Q is 0.40, the Q naught is 1.00, times 1 plus R, to the, and the R was a negative, so it really is going to turn into a 1 minus decimal 0.001, sorry, 3 zeros, 0.000122, and our T, I'll leave as T. I'm going to do a little bit of simplification here. 0.4 is just 0.4, 1 times anything is itself. And then inside the parentheses, I have 1 minus 0.000122, and that gives us 0.999878 T power. Now, I've run into a little bit of a difficult situation because we have the unknown T in the exponent. We've never had a problem like this. We don't know what to do when we have to solve for that exponent. We're going to use something a little bit different here. We're going to use something called a log. And in this class, because this is not a pre-calculus class, we're not going to go into much detail on what this log is or what it's used for. Short story is log stands for logarithm. Logarithms are used to solve for the exponent of an unknown. So we have an unknown exponent of t. Logarithms help us solve for that. What we are going to do, we are going to make sure that we have that number by itself. So if that number wasn't just a 1, we would have had to have divided that off first. So let me show right here. We could have taken this and divided it by the 1. Anything divided by itself is just itself. But once we have that part in exponents by itself, we have the exponents raised to the t power, that part in exponents, we are just going to stick log in front of both sides. Log standing for log or logarithm. That's really what it's standing for. And the nice thing, what happens when we do that, mathematically what's happening is that t is allowed to move to the front of the log. And now we can divide that off the same exact way we were dividing earlier problems when we were trying to solve for the Q. We can take that log, we can divide it to the other side, so we have the log of 0.999878. And notice how I did write down every single decimal place the calculator gave me. I don't want to round that because it's going to throw my answer off. And that's going to give me my t. So in the calculator, I'm going to type in log of 0.4 divided by log of 0.999878. So in your calculator, you do have to find the log button. We are going to have to use that button. It just says log and then type in the number. And when we do that, we get a t-value of 7,510.12. I'm going to round it there because we were talking about years. I'm going to round it to the nearest whole number. 7,510 years. So that tells me after 7,510 years, 40% of the initial carbon will be left. Let's come back up here though and really study what we did. So we started with the equation Q equals Q naught times 1 plus R to the T power. We plugged in our 40%, our 100%. We subtracted off the R because it was a decrease or decaying. This time it's decreasing. We had a simplified expression right here. The second you get to that simplified expression, it's the exponent you're trying to solve for. What we do right away is we stick the word log in front. And then we simply take the log that was with the t and we divide that to the other side. So we had log of 0.4 divided by log of 0.99878. That will be the process for how we solve that t in this class. The formula is not hard. The only new thing we're using is this log. And so we ended up with our 7,510 years. So we do have one new formula in this section. We have to know how to work with this exponential growth function. Q equals Q naught 1 plus r to the t power. This will give us the final amount given initial amount, rate, and time, but we can solve this for any of the pieces that we need by rearranging the problem, as we did in example 3, or in applying this new idea of taking a log using the logarithmic function to solve for the t. We're not really going to do anything else with the log. There are a lot of properties, there are a lot of facts and information about this log. It's a function to itself. We're just doing this very, very basic application with it.